So, hello everyone, welcome to our Capstone presentation. We'll be talking about our designs for drinking water treatment facility with an emphasis on microplastic removal. I'm Paul Mykos.
I'm based in Yandow. I'm Chris Brown.
Emily Cady.
So this is a little bit of what we'll be talking about. First we'll go on and give a background of what microplastics are and why it's such a huge problem that we need to tackle. Then we'll go into the initial concepts of our design and then our actual plans for a final solution. We'll talk about safety, health, and environmental concerns, and then experimental analysis and testing before we delve into some of the economics. So first of all, what are microplastics? They're little pieces of plastic which are less than 5 millimeters in size, and they are a very big problem because they have infiltrated all our water supplies. They have proven to be directly harmful to aquatic organisms. This includes studies showing that microplastics can even penetrate the blood-brain barrier on mussels and fish. And although current studies are still under progress for humans, they have been shown to indirectly be harmful to humans. For example, heavy metals or other chemicals that we know are very dangerous can be absorbed on the microplastics, and these can then be ingested by humans and released in the human body. So you can see here they can be as small as a few micrometers. So unfortunately, microplastics are not only in the ocean, they are also in our tap water that we're drinking or we use to take showers. And here's a study that was published in The Guardian. It's quite shocking that 94% of tap water samples tested in the United States contained microplastics, and there was an average of 4.8 microplastics per 500 milliliters of water, of tap water. And this was actually the highest number found in this study. Then there was another study a year after that showing that microplastics are not only in our tap water but also in our bottled water. So unfortunately, if we can't say, oh, you know, we have microplastics in our tap water, let's shift to bottled water. It's actually worse in bottled water. So we need a fundamental solution. We need to tackle the problem, and to that end, we teamed up and formed a partnership, ECS Consultants. And our goal is to develop a municipal drinking water treatment plant that filters out and effectively removes not only microplastics, but also traditional contaminants. And this should be at a similar cost to existing water treatment processes. So we had 3 requirements for this. Number 1, the process needs to remove at least 90% of microplastics in the water. Number 2, the process needs to make use of existing infrastructure of water systems so that our process can then be adapted to be used in existing treatment plants. And then number 3, the process should not incur additional major costs because then that would increase the water price to consumers. Here are our initial concepts. Initially, our 3 main ideas were using a membrane bioreactor, diatomaceous earth, and reverse osmosis. However, none of them fill all 3 requirements. For example, the membrane bioreactor cannot make use of existing resources and has a very high cost, even though it's effective at removing microplastics. And then we were kind of at a roadblock, but two of our members, Emily and Lauren, attended the New England Water and Environment Association conference here in Boston. And we realized that electrocoagulation has been proven to remove microplastics on a small scale. So we explored this option more. So electrocoagulation can effectively remove at least 90% and up to 99% of microplastics in simulated wastewater, according to literature. Now, what is electrocoagulation? Simply put, it's the use of an electrical current to purify the water. So we have 2 electrodes, an anode and a cathode. The anode releases metal ions inside the water, and at the cathode we have water being hydrolyzed into hydrogen gas and hydroxide ions. The flow of ions from the anode to from the anode to the cathode produces a current in the water, which disrupts the surface charge of microplastics, as well as other contaminants. And this results in complexes forming between the contaminants, including the microplastics and the ions. These complexes then grow to form flux, and the hydrogen bubbles produced in the cathode rise up, carrying the flux to the surface of the water. So effectively removing the microplastics as well as the pollutants from inside our water.
All right. So this is a real simplified block flow diagram for our final design. It is based off of the Cambridge water treatment facility. We actually toured the Cambridge water treatment facility. They were very helpful in helping us decide what we're going to do for our process. And so our design is basically modeled after that. So as if our design is going to be replacing their design in their current state of affairs. And so the first step is the debris filter. It's pretty basic. I'll get into all these later. But the second step is the electric coagulation tanks, which is where the electrical coagulation occurs that Paul was talking about. The water then goes to the rapid sand and activated charcoal filters. And after that, it undergoes chlorination, an inline chlorination treatment, and then it goes to where it's stored before it goes out to the city and to the people's houses. And as I mentioned, it's based off Cambridge, which has 50,000 cubic meters per day of water going through it. So the first part is the debris filter. It's pretty basic. It's just a big filter, or a big filter that keeps contaminants from entering the system from the source. These are big things like leaves and branches and just stuff you don't want going into your process. And they're generally from like 3 millimeters in pore size to 10 millimeters. And they can handle up to 250,000 gallons per minute, which is a very, 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 very large flow rate. Our process only requires 9,200 gallons per minute, so it's more than enough to accommodate our needs. And like I said, after the debris filter, it goes to the electric coagulation tanks. And so electric coagulation takes time to occur. The literature that we're basing this off of had a 40-minute residence time for optimal electric coagulation. So that's what we're running with. And so our design includes 3 parallel tanks. So tank 1 will be undergoing electric coagulation. It's filled with water. The electrodes have current going through them. Electric coagulation is occurring. Simultaneously, tank 2 is draining. It's already undergone electric coagulation. It's draining to downstream. And tank 3 is filling up at the same time. So there's a 40-minute startup period whenever the plant starts up. But after that 40-minute startup period, it's a continuous process through and through. With the flow rates that we are borrowing from Cambridge, that results in about 367,000 gallons over 40 minutes. So we just rounded up to 400,000 gallon tanks for our electric coagulation tanks. This allows sufficient air in case it overfills a little bit or underfills or whatever. For the electrodes, we're using aluminum electrodes. They have been proven to be effective. They're pretty cheap. Not a lot of issues with them. They're pretty good for this purpose. And as Paul mentioned, electric coagulation results in all of the flocks rising to the surface, so they're not actually out of the water yet. So we're going to implement a mechanical skimming device on top of the electric coagulation tanks to actually remove the flocks from the water, which can then flow downstream and go to the rest of the process. After the electric coagulation tanks are the rapid sand and activated charcoal tanks. These pictures are directly from Cambridge. And so the rapid sand filter is basically just gravel and sand. Water is added to the tank, it sits on top of it, and it slowly seeps through. The large particles are obstructed by the gravel and sand particles, so they just can't fit through. And small particles experience some van der Waals forces, so they adhere to the gravel and sand, and they are filtered out that way. And then underneath the gravel and sand is activated carbon, which basically absorbs any remaining contaminants, besides microplastics, obviously. But this is a pretty standard process that's used throughout water treatment around the world. This isn't really what any of our novel stuff is, but we definitely still need to include it. And just for demonstration's sake, this picture on the right is color-coded for gravel, sand, and activated carbon. This blue part is the water that's sitting on top. This is the gravel, the yellow is the sand, and the red is the activated carbon. And so we used this to approximate the sizes of our equipment for our plant. And then finally, we have the inline chlorination treatment, which is 3 different chemical additives. We have bleach, which is sodium hypochlorite, we have sodium hydroxide, and we have ammonia. Sodium hypochlorite has about 220 kilograms per day. This is to kill germs and pathogens. It provides more of a long-term, like it sits in the water, it continues to protect it from pathogens over the course of time, so it's not just like one and done, it's continuous. The sodium hydroxide is mainly for pH adjustment. We use about 3,200 kilograms per day of that. That's a very large amount just to adjust for the pH. And the ammonia is a very, very, very small amount. It's only 10 kilograms per day. And the purpose of that is to form NH2Cl with the free chlorine ions from the bleach, which both kills germs and pathogens. It assists with that, but it also slightly raises the pH, which is not the main point of adding it, but we just felt we needed to include it. And obviously, bleach and ammonia are very bad together if you mix them, but the ammonia is such a small amount, and this is all spread over the course of 24 hours that it's not an issue in this case. And again, this is from Cambridge, just an example. But so when you put all of these together, this is our PNID. On the left, you can see the debris filter, then the 3 electric coagulation tanks, the rapid sand and activated carbon filter, and then this part right here is all of the inline chemical additions. I'm not going to get into it here because I just explained it all, but we do have control systems throughout to ensure the pumps are safe, to ensure the compositions of the chemical streams are what we want them to be, and just, general PNID stuff.
So next we're going to go into a little bit of a safety analysis of our system. So as Mason was talking about with the inline chlorination reactor, the 3 chemicals added are ammonia, sodium hypochlorite or bleach, and sodium hydroxide. So as you can see, they're all relatively hazardous in terms of their health effects, but since they are aqueous, they do not have really high flammability or reactivity concerns. They are used in identical concentrations to standard water treatment processes. That's where we got our numbers from, and also from the Cambridge water treatment facility. So those chemicals are used in the standard concentrations. They're also safely stored in segregated tanks, and they are introduced in line separately. So there's no mixing prior to introduction into the system, so they do not, like the bleach and ammonia wouldn't mix and form chlorine gas, which would be bad. The filter media used, sand, gravel, activated charcoal, also is relatively inert and does not pose a safety risk. So that's one aspect of our chemical safety. We also performed a full hazard and operations analysis on our system. So going through all the different pieces of equipment, finding what the hazards could occur, and then also finding ways that we could implement changes to mitigate those hazards. So through that analysis, we found several major hazards that could occur. The first being electrical hazards due to the electrocoagulation tanks themselves. This would be mitigated by grounding the tanks and insulating the tanks to ensure there's no contact between any plant operators and the actual electrodes themselves. Another major hazard would be debris blockage due to large pieces of debris blocking the filters or the pumps. This would be mitigated by cleaning, preventive maintenance of the filters, as well as making sure our inlet water is as clean as possible. The third major hazard we found was the improper chemical addition. This was mitigated by different control systems, adding the chemicals at slightly different times and at different concentrations. They wouldn't mix prior to addition. Minor hazards include skimmer maintenance, which could lead to improper removal of the microplastics, and hydrogen gas buildup. Hydrogen gas buildup is a concern because it could displace oxygen and cause a poor, low oxygen environment for the plant workers. We would just need to implement proper ventilation to make sure that this doesn't occur. This is our overall HAZOP. As you guys all know, on the left side we have the element of the system where a hazard could occur, moving over towards the right, having the consequence of this hazard and then mitigation for it. I'm not going to go through it fully, but just wanted to show that we went through our system step by step and found the hazards that might occur.
So now onto our proof of concept. We attempted some benchtop experiments. They didn't go so well, which I'll get into in a second, but this is what the setup looked like. We just had a small beaker. We ordered some microplastic beads off of Amazon. They're about 600 micrometers in diameter. They're this small and black. And we ordered aluminum electrodes also off of Amazon, which are just thin plates of aluminum. We hooked them up to a variable power supply, which we borrowed from the physics department. And this is just the setup of a small benchtop electrocoagulation system. And the variable power supply was set to 8 to 12 volts throughout the couple hours we were doing this. There didn't seem to be much of a difference between the two, or between in that range. But basically, it didn't work. For not that the technology worked, but the materials were not adequate. In this picture, black again is microplastics. The white are bubbles that are formed from the electrocoagulation process. And as I mentioned, the microplastics are 600 micrometers in diameter, which are not the target of the electrocoagulation system. We're targeting much smaller microplastics that are prevalent throughout all the water systems that make it through the rapid sand and activated charcoal filters. Microplastics of these size wouldn't make it through the activated charcoal filters. They would get caught up. So these were too large, which was evident here. In that red box, you can see a flock. It's a bunch of bubbles and a bunch of microplastics, and they're suspended on the bottom of the beaker. It's good because it shows that electrocoagulation does cause flocculation. It does cause particles, the microplastic particles, to flock to the bubbles. But in this specific case, the microplastics were too heavy, they were too large. The weight of them in the flock outweighed the force of the buoyancy of the bubbles, so they didn't rise to the surface. And so the pros of this is that the technology does work, it is good. The cons is that we aren't able to run benchtop experiments to find any operating parameters or specification limits for our process, because our process relies on removing the microplastics from the surface, which we're not able to simulate due to budget constraints.
Yes, so because of kind of the limitations of the data we were able to get in the lab, we moved on to simulating our process, and we used a software called ANSYS, which is a CFD or computational fluid dynamics software. It's one of the standards in the field. It's a lot of what mechanical engineers use, especially when modeling transport processes or various flow diagrams. And they also have an electric component, so you're able to model kind of electric flow. So one thing that we wanted to get from this was how to set up the electrocoagulation tank. That is the really novel step. People have done electrocoagulation and proved that it works for drinking water and microplastics removal on a small benchtop scale, where they just kind of did what we did and they just kind of stick the electrodes in a little beaker and call it a day. But when you put it on a much larger tank, you need way more electrodes, and how you orientate them matters. So what we did was we kind of thought of different methods of orientation. This is kind of modeling what they do on the lab scale, where it's just along the edges, and then we did kind of this serpentine snake-like configuration, and then we just did them kind of stacked or then a little bit scattered. And all of these were initially made in SolidWorks, so they have all of the exact same base tank, and all of the electrodes are the same diameter and are relatively spaced evenly. These ones are spaced a little bit further apart just because of ANSYS restrictions, but they all had the same voltage applied to them. And so as you can see here, this red area shows that has the smallest voltage dissipation, and so that is the electrode configuration that we decided to go with. The next thing that we wanted to do with that, though, was, okay, great, we want to put them in the serpentine pattern. How many electrodes do we need? How far should we space them apart? So what we did was we based on the literature data that showed that a current density of 19 amps per meter squared would effectively remove all of the microplastics. And so we said, great, I want that current density, but I don't really care how much voltage I have to add to it or how many electrodes I need. So I started with separating the electrodes 30 centimeters apart, and then I did all the way up to 3 meters. And you can see on this curve that when they're really close together, that you need a lot of electrodes because they're also sacrificial electrodes, so you need to replace them every 150 days of operation. You only use them for 40 minutes out of every 2 hours because of the system that Mason mentioned, so you need to replace them about 1.2 times a year. We did round up to 2 because, things happen. So here, the cost of the electrodes completely dominated. And then over here, you use much fewer electrodes, but the electricity that you need to create that same current density is a lot higher. So the electricity costs started to dominate. And so at the bottom here, you see at about 110 or 1.1 meters apart is the kind of optimization of that electrode cost and the electricity cost. So the other thing that we wanted to look at is kind of the overall electricity cost for the project. So every water treatment facility has the major electricity and utility cost of pressurizing the water that you get from the lake or the whatever pond and then you need to pressurize it to people's houses. So the tap water pressure is between 40 to 45 psi, has to be below 60. But however, they pressurize it to a lot higher than that in the water treatment facility, which then loses its pressure through the various unit operations. So the cost of pumping that electricity is about 95% of our total cost too. The cost in the electric coagulation tank is very negligible in comparison. Additionally, the general kind of water treatment plant in that sedimentation tank that we're turning into the electrocoagulation tank, they need to use this compound called alum, and they use it because it does the same thing. It creates flux. However, it doesn't remove microplastics because it's heavy, so it sinks to the bottom and the microplastics float. But the research and literature say that with electrocoagulation, you no longer need this alum, and that's good because while alum's really, really cheap, you need to use a lot of it. You need to use about 600 gallons a day. So the cost of storing all of that alum, pumping it, costs about $7 million a year, which is significantly less than the cost of the electrocoagulation tank. So our process wouldn't cost any more, and theoretically, if you can get rid of this alum, it would cost less.
All right, so taking all of this research and this process that we've created, we've decided to form a company and call ourselves ECS Consultants. We've chosen to be a limited liability company due to our small company size and not really a need for a corporate structure. We are an engineering design firm, which means we are contracted out for specific projects by these water treatment facilities. And all these projects and processes are done on a by-case basis for whatever facility we're designing it for. All companies working with water treatment facilities have to be registered through the Board of Certification of Operators of Drinking Water Supply Facilities, which we plan on doing. Our biggest strategic advantage is that we are the only company that we could find looking to remove microplastics from drinking water. There is not any other company out there that we've found that are able to remove microplastics from tap water on a large scale for a cost that's very similar to conventional water treatment. Based upon our Mentor's knowledge and industry standard, our consulting fee is 10% of the total ISBL and OSBL cost. So there are two different sides for the economics of this. There is the economics with regards to the city and the water treatment facility, the cost that they incur, and then whatever cost is incurred by the city directly affects the design firm's revenue, which is our consulting fee. And so I'll sort of discuss the costs and things associated with the city and then the costs and revenue associated with the design firm. But going through here, some of the costs incurred by the city are the major equipment such as the tanks, the pumps, things like that. Construction of the facility if it's not already there, or renovation of the facility if it is. Utility costs such as the electricity that Emily mentioned, as well as our consulting fee. The cost incurred by the consultants is the labor in designing the facility and the process, any software needed for designing the process, as well as just conventional office space, office equipment, computers, things like that. So according to our engineering design textbook from last year in Capstone, the total ISBL and OSBL cost, if we assume our 18.25 million metric tons of water per year that's processed, is around $477 million. This cost is incurred directly by the city. Inherent in this cost is a 30% uncertainty, so there is a wide range of error in this cost. It is a very high level estimation, and you'll see in a moment that this cost is likely much lower than what we've calculated here. This table shows the major equipment cost of the different equipment in the facility that we are designing. The biggest cost by far is the electrocoagulation tank at $12 million, but I want to draw your attention to the very last row. All of these major equipment pieces comprise just 5% of the total ISBL cost. This is a very low percentage, and this means that it is very likely that the ISBL cost is much lower than what we've calculated. These are the operating costs that are incurred by the city. They include the electricity and chemical disinfectant. They do not include any labor cost or maintenance cost. And you can see that it's relatively inexpensive. The electricity and chemicals per year come around to $200,000. So this is a income statement and revenue for the design firm now. So these are the costs and revenues of the design firm, not for the city. As I mentioned earlier, our consulting fee is 10% of the total cost. We've assumed that the cost we estimated earlier is the cost going forward for accounting purposes, which is 10% is $44 million. We are also assuming a couple things in this income statement. The first one is that we are contracted for a project and that the project is completed and payment paid in full in December of that year, so a full 1-year project timeline. Additionally, we are assuming this is the first year of operation for the company, and because it's the first year of operation, it is likely we will need a loan to get up on our feet and running. So let me draw your attention to the income statement. All right, so that's the 10% that I was speaking about earlier in the revenue. And then we estimated that we will need a loan of around $700,000, give or take. So that is a cash inflow, and that gives us a cash inflow of $45 million. And then we have our operating expenses of the design firm. We're assuming 5 engineers, $200,000 a year for a salary. Sounds pretty good. So those are our salary expenses. Administrative expenses include the software, like I mentioned, computers. That is what we need the loan for. So those are both cash outflows. And then at the end of the year, we have a loan expense. We are assuming a 27% loan compounded annually, and that this loan is paid back in full, both principal and interest, at the very end of the year. So that is a cash outflow. We are assuming a 21% corporate tax rate, which gives us a net income after taxes of around $33.8 million, which is wildly profitable. But also keep in mind that this is assuming that this ISBL number is as high as the calculation says it is. We saw that it's very likely that the calculation is much lower than that, and so our net income is very likely lower than $33.8 million.
So after all of those numbers, a quick recap would be helpful. So what we wanted to kind of drive home is that our proof of concept experiments did not fully show that we could remove the microplastics, but they did show that we could flocculate them. And if we had the correct materials, with a higher budget, we could remove the microplastics effectively. We were also able to show that using ANSYS, we could design the electrode configurations. So with all the different optimization that we did, we landed on this serpentine design here. This provides the greatest current density throughout the tank, leading to greater microplastic removal. We were also able to do an economic analysis and show that the ISBL and OSBL cost for the treatment plant as currently designed is $477 million, while this would likely be decreased. And our consultancy fee would be 10% of this cost, roughly $47.7 million. So in conclusion, we wanted to go back to those 3 initial criteria that we defined at the beginning of our project. Electrocoagulation meets the first criteria because it has been shown in bench scale studies to remove up to 99% of microplastic waste. Therefore, meeting that criteria. Electrocoagulation meets criteria number 2 because it can be implemented in existing treatment plants. We decided for this project to design a treatment plant from the ground up. That would be a city wanting a new treatment plant, maybe replacing an old one or a new facility in a new spot. But it could be implemented in an existing sedimentation tank. We would need to design it for that sort of situation, but it could be criteria number 2. Criteria number 3 was that we wanted to incur minimal additional cost. And as we showed through the economic analysis, the resulting water would be either the same cost or slightly cheaper than current water treatment processes. So, and also, 7% of the operating costs were electrocoagulation, not really a greater cost due to the electricity. So it meets criteria number 3 as well. Finally, just some acknowledgements that we wanted to go through. We want to thank Ed Dowling at the Cambridge Water Department, who was very gracious in giving us a tour, and kind of the basis for our project was that tour. We also wanted to thank Barris Alton-Kynek at the Physics Department for lending us the power supply. Also, Caroline Miller and Hadley Seaman for their expertise and help with the ANSYS design of the electrodes. Jeff Heel, our mentor, was very helpful with the economic analysis. And then finally, Professor Pfluger for all of her help, all of her comments, and all of you as well.
Just out of curiosity, do you guys know what the method used was to determine the how much microplastics were in the water? Like on the first slide, it was published in the magazine.
Yeah, so they stained. They used a certain stain, I don't remember, they stained the water so that the microplastics and microfragments are visible. And then they concentrated the water, and then they counted them under a microscope, electron microscope.
Did you consider reducing the particle size of the material that you received?
Yeah, we tried. We tried grinding them down. We were considering taking like a soda bottle, like a Mountain Dew bottle, it's already green, and like shaving it down to get tiny plastic fibers. None of it was really working. None of it was feasible. And like there were some microplastics online that we could buy for the entirety of our budget. For one small batch that was like 5 micrometers, I think.
Yeah.
But if we bought those, we wouldn't be able to buy anything else for the experiments, like electrodes and stuff.
Right.
So that wasn't feasible, and nothing else really worked out. Yeah.
Yeah.
Thank you.
So it was due to budget constraints mainly that we couldn't get the actual materials.
Can you back to your revenue slide? So your revenue's 44 million, but I thought you would only be making 10% of that amount.
That is 10%. So the total ISBL and OSBL cost is 447 million.
Okay.
So 10%, 44 million.
Let me understand now, this 447 million is the cost of the entire plant from the beginning to it goes out to the, okay.
Yes.
What you're developing though is just the electro coagulation section, right?
No, that's sorry to interrupt, but that's what we initially wanted to do. But the specifications and like the water treatment facilities throughout the U.S. are so vastly different in their size and their requirements and the quality of the water, and because of that, each individual water treatment system is going to be different from one another. And so rather than, for this project specifically, rather than just implement the electrocoagulation section, we designed the whole plant. So all of this is as if we built the entire plant from the ground up at Cambridge.
Yeah, but there's a lot of companies that do everything else besides the electrocoagulation section, right?
Yeah.
You expect to compete with them?
Well, yes and no. Like I mentioned, our initial idea was just look at the sedimentation tanks are already widely used, and that's basically a big tank that is used to have the particles inside sediment down into the bottom. And our idea was to just make an implementable electrocoagulation device into that, like you're talking about right now, and have that widely distributed and sell that as our product. But when we were doing the business analysis, it wasn't feasible because it wasn't one size fits all. It wasn't like you could scale it up in different ways. It wasn't like it would have, if we made that, it would be specifically for that one case, and we would have to redesign it for other cases. So this design is specifically for this one location based on the water chemistry there. And that's why we're the designing firm. If we were hired to do something in Illinois or something like that, or a water treatment facility in Texas, then we'd have to redesign it again.
So to jump off of that, I do kind of want to answer your question and say that we would be competing for the contracts to design the water treatment facility as a whole. And we would think that the communities, the cities would want to go with our product because it would remove microplastics and they would want to pass that on to the consumers cleaner water.
I guess I have a problem with the concept, your business concept, of thinking you're going to build and sell the whole plant. As a project, as I would look at it, and what you bring to the table in terms of the technology is that electrocoagulation section. And I think as a business plan, that's what you should be offering to the communities and to the existing design firms that were out there. Because I've participated in the waste treatment side of this business. I've never participated in the water purification side. But when you're dealing with a municipality, it's a brave new world. They have their friends. You don't go into this business as a newcomer, okay? You gotta be partnering with somebody. So the concept of being able to add a piece in the middle, I think you're gonna get somebody to buy the whole process. In my mind, it is unlikely. I think you would focus on the electrocoagulation section and look at what your profits would be on that, either as a consultant or as offering the specific design with your electrodes. That's my thought. And one other thought too is, how much more space does this electrocoagulation take over? Could be more specific. Could you fit this technology into Cambridge?
Oh, yeah.
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 Good, okay.
In the existing tanks.
Go back to the
Well,
picture that
I'm
we
talking
had
about,
here.
say, the flow area. Is there adequate flow area, adequate space in Cambridge to put these coagulation tanks in?
Yeah, we kind of glossed over this, but an electrocoagulation tank that we're designing is basically a sedimentation tank, just modified with the electrocoagulation technology. And sedimentation tanks are already in use everywhere. It's just, instead of sedimentation and alum and all of that, we're using electrocoagulation in the same tank, in the same kind of area or
So-
volume that you're talking about.
So you're expecting the flux to go to the top and the sedimentation to go to the bottom?
No, we're not sedimenting anything. That's what they're currently doing. We're
Well,
replacing it.
then you have to replace those sedimentation tanks, don't you?
No, because
No.
the sedimentation tank, all it is a giant tank. This is the rapid sand filter, but it's basically the same thing, where it's just a giant hole, and they just put the water there, and they dose it with alum, and they just let it sit for
Yeah.
generally about 2 hours.
Yeah.
And so instead, that giant tank, instead of dosing it with alum, we would just put the electrodes in it and put electricity in it and have it sit instead for 2 hours for 40 minutes, and have the sedimentation, instead of sinking to the bottom, it would just rise to the top.
So you're talking about flocking everything, even with the larger particles?
Yes, because
But you showed me your experiment where the larger particle ended up in the bottom, even in your...
Well, that's fine, because they get, after the electrocoagulation tank is the rapid sand and activated carbon filters, where the larger particles get filtered out there anyway. So we're not targeting those, we're just targeting the smaller
So
particles.
these sedimentation tanks are before the carbon?
Mhm.
Yes.
Okay.
Okay, so, well, you already answered that one. How big, so you talked about the way that you would do the electrodes. What are the dimensions?
sure, do you want me to?
I don't know if I'm.
Okay, just go back, yeah, you can go
Yeah.
back to the slide. So this slide, these dimensions of the tank are a bit smaller than the full one. When the next slide, I did the full-size tank.
Yeah.
The reason I did that is because ANSYS works by putting on mesh over the full-size tank. And so the bigger the tank is, the longer it takes. So for this, I was trying to figure out how to use ANSYS. So I scaled it down where each of the dimensions have the same ratio as they did in the full tank. They're just scaled. And then for when I was trying to figure out how to space the electrodes, I used the full-size tank. So this, in the full-size tank, is the dimension you don't see, which is the depth is 23 meters, and then it's 11.25, and then 5.75 meters is the size of the tank. And then the electrodes in the final configuration, there are 9 of them, and they're spaced 110 centimeters or 1.1 meters apart, and they are, I think, 4 centimeters thick. So.
How do you dispose of the microplastics and everything else?
So it all rises to the top in this sludge, and so it would be disposed of kind of the same way the sedimentation tank is now, where it's actually easier to dispose of because it's not on the bottom of the tank, so you don't have to clean it, you just have to skim it off the top. And then depending on how kind of wet the cake is what they call it, sometimes you have to dry it, a lot of times you don't, which is why we include it in here. And then unfortunately you do have to just send that to a landfill, so like that's not the most environmentally friendly aspect of it. But because we aren't kind of taking the microplastics out by themselves, you can't just recycle them because you're kind of taking them out in a bulk with a bunch of other things.
That seems counterintuitive to.
Yeah.
Well, we're removing them from the drinking water, at least from the tap water.
So would you guys be relying on like a government initiative to force the removal of microplastics? Because I don't know if there exists today like contracts up to replace entire water systems with something that removes.
Eventually, if it comes to that, but microplastics is a real rising concern. There's articles coming out left and right, studies done where like they pull 50 animals out of the ocean, and out of 50 of them, 50 animals have microplastics like in their brains and their stomach and their linings and stuff. So we're hoping that people and the concern of people, or the people's concern of ingesting these microplastics comes first. But if that doesn't happen, then we would probably end up relying on government grants and stuff.
Yeah, and also that's why we looked into the cost of it, where we wanted to make sure it didn't cost exorbitantly more, because there isn't a government, forcing you to do it right now. So that's why we looked into kind of mitigating the cost with if you don't need to use the alum, if you don't need to use other things. So even if you do need to use the alum, overall it's going to increase it by about $100,000 a year, which is pretty negligible, especially because the MWRA, who charges water to Boston, is about $3,500 per million gallons, and you're producing 12 million gallons a day times 365 days a year. So the amount that it's going to increase is pennies. So that's kind of the two aspects we were looking at with that.
There are also some articles, so California is actually starting to look at this, and they will put specifications on microplastics in water. So it's definitely a rapidly rising concern.
Just a question on these figures up now. Is that the color scale voltage or current? Or?
So this is current. I kind of did this versus the ones that I didn't think to bring you guys, but of the separating the electrodes, I did them slightly differently. For this, I put the same 5 volts on each of them so I could kind of directly compare which one had the best voltage dissipation. For the separating the electrodes by distance, I also added voltage, and because ANSYS knew it was water, it could output me current density. And so then I could check, okay, the minimum is greater than this 19.2, which is what the literature had shown removes microplastics. So this right here is voltage.
Okay, and just a follow-up question. Are you flowing the water through the electrode, or is it just the electrode?
Yeah, it's stationary. So what we did was kind of like a semi-batch system, where that's why we had the 3 electrocoagulation tanks, where there is constantly water running through the system, but it's coming from different tanks. So it has a 40-minute residence time where it just sits there and undergoes electrocoagulation. And during that 40 minutes, a different one of the tanks is draining and adding more water downstream, while the third is filling and taking water from upstream. So there's always water running through the system, but the electrocoagulation happens on a stationary water.
Okay, so that the system you chose would have 2 of these plates kind of parallel to each other in just a batch type tank.
Mm-hmm.
That water in between would be stationary?
Yep.
Okay, thank you.
Excellent, thank you very much.